Okay, hopefully you would have seen the first lesson on the photoelectric effect, and now we're talking about energy levels. We are going to use all those ideas of the photoelectric effect, but now think about how electrons move about atoms, and how they might be excited to higher energy levels or lower energy levels. Right, simply, there is my nucleus. It's positive. I've drawn it terribly small, but it's a positive nucleus from all the protons, and then around the outside we have energy levels. And we have a huge number of these energy levels. And an electron sits in the lowest energy level, not drawn to scale of course, and then orbits around the proton. It could be more than one proton. We're going to use hydrogen here because it's the simplest element to use. Okay, it moves around there. And at some moments, put it this way, that electron can move up to higher energy levels, any one of those energy levels, or even all the way out until it's ionized. Ionized meaning the electron has been released from the atom. So let's just jot down the important words there. So electrons prefer the lowest energy state, but can occupy any of them. Good. In order for it to occupy higher energy states, it must gain some sort of energy. So to occupy higher energy states, it must gain energy. Okay, I think it's easier to draw, rather than to look at the electron orbiting an atom, but to sort of almost cut it down here, unsplit it, and separate it out into a nice straight line. So what we'll have here is we have one energy level, which is the bottom one, the next energy level up, and then subsequent energy levels above that. And you'll notice that they're getting closer and closer, and that's exactly what happens, and I'll try and explain later why that is, until we get to the last one, which is n equals infinity, which is ionization. This is when an electron leaves an atom. Leaves the attraction of the nucleus, if you will. And each shell around the outside has an energy level associated with n equals 1, n equals 2, n equals 3, and so on and so forth. And this can be any number all the way up to the very end where it's ionization. The bottom one is called our ground state, our preferred energy level if the electron has not been excited in any way. Okay, there are many ways in which well, not that many, let's say there's a couple of ways in which this electron can gain energy. The first one is if another electron comes in. So an electron comes in and it can strike that electron. Also, another way that might happen is a photon might come in and strike that electron. Okay, two things happen when energy is transmitted to the electron. It either jumps up one state or many states, or indeed it breaks off and it ionizes. Good, now that can be a photon or it can be an electron. The important point is, if it's a photon, the photon needs to be exactly the same energy as the difference in these energy levels in order to cause that promotion. And subsequently afterwards, the photon disappears. However, an electron can come in, can knock this electron that's bound around the atom, promote it, and any energy left over is that which the electron takes off for itself. And we're going to deal with each of these in succession. So let's imagine, so let me just write those down again. One, so excitation occurs. Excitation stroke ionization occurs in two ways. One, with an electron. Two, with a photon. Okay, let's take number 1 first. Let's say an electron is inbound. Okay, so an example. Okay, we've got an electron. It comes in with an energy, kinetic energy of 6 times 10 to the minus 19 joules. And then in the first instance, it causes ionization and is left with, let's say, 4 times 10 to the minus 19 joules. So it's caused an ionization, it's kicked out the electron completely free from the atom, and it's left with some. And in example B, it causes an excitation and is left with 5 times 10 to the minus 19 joules. The question is, what's the energy of ionization and what's the energy of the excitation? If you think you know, hit pause, otherwise here comes the answer. Okay, first of all, right, for the answer to A, all we're looking for really here is the difference in energy. If it came in with 6 times 10 and it's left with 4, then whatever's the difference is going to be that which the energy of ionization. So the energy of ionization is going to be 6 times 10 to the minus 19 minus 4 times 10 to the minus 19 gives us 19 joules. That's the energy of ionization. If we need to convert to electron volts, which I didn't say, but it'd be nice quick to do so, 2 times 10 to the minus 19 divided by the 1.6, which is the energy per electron volt, gives us 1.25 electron volts. Okay, let's take a look at B. What's the energy of excitation? Once again, you're just looking for the difference. 6 times 10 to the minus 19 minus 5 10 to the minus 19 gives us 1 times 10 to the minus 19 joules, which is the same as, if I quickly make the conversion into electron volts, I'm dividing by the number of joules per electron volt, gives us 0.625 electron volts. So this is straightforward, and it's not that different to dealing with the photoelectric effect when the energy came in and out of the photon and the work function. But do remember that we can have either an electron inbound or a photon inbound, and it causes movements in energy or ionizations. Okay, let me try another one. Let's say that this time we have what happens after the promotion occurs. So here is my atom again. Let's imagine that I've got an electron in a higher energy state and it falls down to a lower energy state. What happens here? Well, a photon is given off. And the energy of that photon is the equations we've been using in the previous video, which deals with the photoelectric effect. However, the important point here is the energy of that photon is actually the difference in energy levels between the higher to the lower energy levels. So there is a difference in the energy. Okay, bear that in mind. That's the equation we're going to be making use of. Let me give you an example. I prefer, once again, as I've said before, to unravel this, to split it and stretch it out. And so therefore, I have these lines of energy. Here's my energy of ionization. Here's my first one. And I'm going to put some values to these as well. I'm going to say we're running at, let's say, 10.4 electron volts. I know it's not actually, if you look more carefully, that's strictly not true for a hydrogen, but let's just work on that. We have about 5.4 electron volts, the next one up, and 1.8 electron volts further up. Okay, so the question is, what happens as we move from energy level 2 to 1 to start with, and what will be the frequency of the photon produced? If you think you know, hit pause, otherwise here comes the answer. Okay, the energy is going to be equal to the difference, which gives us 5 electron volts. That's quite neat and straightforward. We need to convert that, of course, into a number of joules. So we multiply it by the energy on 1 electron volt, which converts it into joules quite nicely at 8 times 10 to the minus 19 joules. A hard part done. The rest is what we've practiced before. We can say that E is HF, therefore giving us a frequency of G over H, which is 6.63 times 10 to the minus 34, 1.2 times 10 to the 15 hertz. I hope you can see that. Sorry, it's so small. It's 1.2 times 10 to the 15 hertz. Okay, second point. What happens if we were moving to 3 to 1? And therefore, what's the wavelength associated with that transition? If you think you know, hit pause. Otherwise, here comes the answer. Very simply, the energy is going to be equal to hc over lambda, another variation of our equation. So therefore, the wavelength is hc over the energy difference, the difference in moving between the two. Let me just draw an arrow in there because that's quite useful. That's the energy change, and in the first one, that was the energy change, which is associated with a photon, which is associated with a photon. Okay, back to this one. So, simply, let's substitute 663, 10 to the minus 34, 3 times 10 to the 8, divided by, of course, the difference in energy, which is 10.4 minus 1.8, and let's convert it out of electron volts into joules so we know the equation works. And that gives us a wonderful... Let me just tap it into the equation. I don't have that one off the top of my head. It's going to give us something like 6.63 x minus 34, 3t8 divided by that was done very fast. Hopefully it's come out with the right answer of about 145 nanometers, or I should probably encourage you, I don't like it written like that often, 1.45 times 10 to the minus 7 meters. Okay, you might want to double check that for me and tell me if I'm right or not. Good, so we have these transitions. This is the D excitation. Okay, now I did mention before here that these electrons can be struck by photons themselves. It doesn't mean an electron that strikes this bound electron, but a photon can strike it as well. If the photon were to strike it, it needs to be precisely the correct energy for that gap, and there's no electron afterwards. Photon afterwards, sorry. So let's look at an example of that. Let's look at let's use the example of okay, I'll do two. I'll draw a big drawing here. Okay, this is our electron. Inbound is a photon, and it promotes it to the higher energy. The change in energy here equals exactly the change in energy there, and nothing. There is no photon afterwards. Here is our proton in the middle. So, how do we describe this? This is a really useful one to describe, and I'll explain why right now. Here is our energy levels. And these energy levels can be incredibly complicated depending on what element you've got going on here. Let's give us a 5.7 electron volt level. Obviously this is the bottom, n equals 1. These can be magnitudes as well, they don't need to be in the correct way around. I'll put this at 3.9 electron volts, n equals 2, nominally, I call these. And let's imagine a photon comes in and causes the electron to jump from bottom to top. Okay, how much energy has that caused? And also, what type of light? What's the wavelength of light? So first of all, energy and wavelength of light. If you think you know, hit pause. Otherwise, here comes the answer. Okay, so the energy is going to be the difference in levels, which is very simple, 5.7 electron volts, which is the same as, in terms of joules, it's going to be riding at about, numbers again, hold on, 5.7 by 9.12 times 10 to the minus 19 joules. Okay. What about the wavelength? Well, we know the wavelength is hc over the energy level, which gives us, and I'm running out of space, so all I will do is I will plug in, I will say this is hc over the answer from here. So it's oh, that's way out. Okay, let me try that one more time. Good. That's about 2.18 times 10 to the minus 7 meters. In other words, about 218 nanometers. Now, let's just work through this problem to completion. Now, hopefully, you should know that the electromagnetic spectrum runs from, let's go from red, orange, yellow, green, blue, indigo, violet. So Richard of York gave battle in vain. And on these two ends, good little indicators to know are 700 nanometers all the way through to about 400 nanometers. Now, the reason I write those down is because that's visible light. So anything that reaches off this way will be ultraviolet, and anything reaching off this way will be infrared. So if you bear those things in mind, I don't know why I've drawn that there, that makes it terribly confusing. This is an ultraviolet light is absorbed. Now, let's look at these two transitions that occur. One there and one there. The n equals 3 to n equals 2. Let me just write that down. N from, let's look at the energy from 3 to 2 and its associated wavelength. And then I'm interested in the energy levels from 2 to 1 and the associated wavelength. So if you think you can work those out, hit pause now, or here comes the answer. Right, so 3 from the 2, we're going to say that wavelength is hc over E. I hope you picked that up from previously in the video. I won't go over that again. So 6.63 times 10 to the minus 34, 3 times 10 to the 8. Divide that by, now we needed the change in energy here, which gives us, I said 3 to 2, so that's 5.7 minus 3.9, and then convert from electron volt into joules. And that should give us, if I went from 2 to 3, type this quickly into the calculator again, and then we should hopefully see a wavelength which is not that far off visible light. Okay, good. That gives us 6.9 times 10 to the minus 7 meters, or 690 nanometers. So we can see here, 690, though it sits near the red, still falls in visible light. Okay, what's happening on the other side if we go 2 to 1? Well, we can work quickly on this now because we've practiced. 3 to the x be 8. Divide that by, I'm now looking at the 2 to 1, so it's a 3.9 energy gap, and that should give me something in the order of, just to be absolutely sure, I'll work it through again. Yeah, That gives me something over 318 nanometers. Okay, so what we've done here is ultraviolet light has come in and been absorbed, so invisible light's come in and been absorbed, and yet that electron, in transitioning down and transitioning down again, has given off visible light, has absorbed invisible light. So invisible in, visible, visible. So this is why we call it fluorescence. Fluorescence. That's why things fluoresce. They look as though they're glowing. We don't see what light they've taken in because it's invisible, but they re-emit in the visible spectrum. Okay, importantly, mercury vapor lamps look like this. So the tubes on ceilings, they are mercury based. With a vapor. They absorb ultraviolet light. Sorry, they emit ultraviolet light. And then the coating on the tubes the white fluorescing bits absorb the UV and emit visible. Okay, 3 important points. So tubes on the ceiling, the mercury-based vapor, they emit UV light. The coatings on the tube are white, but they absorb the UV light and emit in the visible. And I suppose I'll just say in here as well, how that's achieved, the mercury-based vapor, electrically. Excite the atoms. So that's why I put electricity through it. Okay, good. And the final thing, I suppose, we're going to talk about here is one of the 2 final things is that with all these energy levels, which are very specific per element, I'm running out of ink. So all these levels, which are very specific, we have. Okay, there we go. This is a fingerprint of an atom. They're all very unique. So all these transitions that occur, and they regularly occur, very, very fast. Any of them will occur. Give rise to, if you look at it through a prism or a spectroscope or a diffraction grating, all of those photons which are given off, which are very specific with specific energy levels, give rise to line spectra. The line spectra, of course, has a wavelength, and the different colours give rise to those photons. Good, and you can work out the colour of light, and hence from the colour of light you can work out the energy transitions, how unique the element is. I suppose this is how helium was discovered. And helium wasn't found on Earth. However, the photons that came through but looking at the sun, they noticed dark lines, not bright lines, but dark lines, implying something was absorbing the light coming from the sun. And so therefore, the sun, Helios, meaning sun, meant that they knew about helium before they actually discovered it on Earth. This is how they see the stars and what elements are in the stars. Very finally, I should say, and this is a slight extension, you won't need to worry too much about this, but here we go. We're looking now at specifically hydrogen, and with hydrogen, these energy levels, which we're familiar with, follow a really, really easy rule. And the rule is that the energy level is 13.6 electrons followed by n squared. N being the energy level. giving us something like a 13.6 electron volt level. The next one's a 3.6, then a 1.5, 1, 0.86 electron volts, etc., 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 etc. Up to ionization. In actual fact, any transition from any of these levels down into the n equals 3 gives rise to infrared, which is also known as the Paschen series of light. Any of those transitions down into the second one give rise to the Balmer series, which is the visible, hence it was discovered first. And any of those transitions similarly down to the last one, because I've got such high energy, are known as the Lyman series, which are ultralight. Okay, I think that's enough information for now.